Hello, everyone. So far in this course, we have done a bit of a review or recap of electrostatics and magnetostatics. So now it's time to look at the full electrodynamic problem. And so now basically we move on to consider more general situations where there can be both electric and magnetic fields, and both electric and magnetic fields can depend on time. So we begin our discussion again, starting from the Maxwell's equations, which again we are assuming that these are the fundamental equations, which is the starting point of our discussion. And the local form of the Maxwell's equation, these are the fundamental equations, which is the starting point of our discussion. And here now we are going to consider the electric and magnetic fields that are functions of both time and spatial coordinates. Okay, so earlier, as we saw in magnetostatics or in electrostatics, the time dependence was not there, and if the time dependence is not there, then the equations essentially decouple and we can treat them differently. That's why we can treat the electric fields separately in electrostatics and the magnetic fields separately in magnetostatics when things are time independent. But now everything depends on time. So we move on to the most general electrodynamic problem, which basically tells us that we need to look for solutions to this coupled partial differential equations. Okay, and of course, along with these Maxwell's equations, we also have to specify the Lorentz force density, which is given by this expression, the charge density times the electric field and the current density across the magnetic field. This is the force that charged particles experiences when they are exposed to electric and magnetic fields. Okay, so this is also happens to be one of the fundamental starting points. So together with the Maxwell's equation, so the Maxwell's equation tells us how the electric and magnetic field behaves in the presence of charged particles. When they move around and they form some current, how they will behave, how the E and B fields behave in the presence of moving charge and moving charge in general. And on the other hand, the Lorentz force density tells us how the electric and magnetic fields tend to affect the charges, which themselves create the electric and magnetic field. So this is more like a coupled problem where there are exchanges between the charged particles and the fields. Okay, so this is the starting point again. And so again, we are now looking at the most general. We are not making any special ansatz. We are looking at the most general electrodynamic problem. And given that these Maxwell's equations exist, there is a consistency condition on the sources, as we have stated again. Previously we had a elaborate discussion of this. This consistency condition is essentially a conservation of charge, and in the local form, this conservation of charge can be written in this way: that the time derivative of the charge density plus the divergence of the current that vanishes. Okay, so this is the statement of conservation of charge. As we'll see later on in this course, that this at the moment we are trying to say that it follows from the consistency of the equation, but there's a deep symmetry principle. There's a symmetry principle which is responsible for this charge conservation principle to exist actually. Okay, so this deep symmetry principle, a little bit of it you have already encountered in magnetostatics. And again, as we proceed along the course, I will try to go on fleshing this out, and slowly we will discuss that when we do the relativistic formulation of electrodynamics. So with that those introductory statements in place, let us today look at just one of these equations, and this is this Karloff-E equation. Okay, sometimes people also refer to this Karloff-E equation as quote unquote Faraday's law, and we'll see that how much of Faraday's law has got to do with this equation, and how much of Faraday's law is different from this equation. Okay, so that is our main objective today. It is to study this equation closely and to see or to study Faraday's law and to see what is the relationship of Faraday's law as Faraday had stated it with this particular local equation. That is what we will explore today mainly. So this is the equation that we are looking at, and if we take this equation and if we integrate it over some surface S like this, through which, let's say, some magnetic field is going, then this magnetic field is basically, so if we integrate it over the surface, then we get the magnetic flux through the surface. So that is some this thing, and if the magnetic field is changing, then the magnetic flux through the surface would also be changing. And if we consider the surface integral of this curl of E, that by Stokes' theorem would give me the line integral of the electric field around this curve C, which is basically the boundary of this surface S. Okay, so that is what we will get if we integrate this equation over a surface S. Okay, on the left hand side we'll get the flux, which I denote by phi. It's the flux of the magnetic field through the surface. Okay, and this time derivative of that is going to remain. Okay, because we are integrating the space coordinates, so this partial derivative with respect to time essentially becomes a total derivative with respect to time, because this one only depends on time. Okay, so this magnetic flux through the surface S, this is this integral, this is the surface integral of the magnetic field, and on the left hand side we have this line integral of the electric field. Now, as we know very well that the electromagnetic force exerted by the electric field on a charge is Q times E, and therefore the line integral of the electric field can be thought of as the line integral of the force per unit charge. So if we define this quantity as force per unit charge integrated around the closed loop, then that quantity is called EMF, or this full form of electromotive force. And again, this is not really a force exactly, but it's force per unit charge integrated around the closed loop. Okay, that is what it is. Okay, and you take E and you basically do the line integral of E around a closed loop. That is going to give you the EMF which is generated in this closed loop if there is a conductor in the closed loop. Okay, so basically, if the idea is that to summarize, so in general, in a situation there can be a changing magnetic field, and you can always draw loops like this where there will be electric field. So this equation, therefore, this local equation tells us that changing magnetic field essentially gives rise to some kind of an electric field. Now, if there is, let's say, some kind of a conducting wire along this loop, okay, then this electric field will produce a force per unit charge on the charged particles living inside this conducting wire, and that would result in a current flowing through the wire. So this EMF has the potential of driving a current through a conductor if there exists a conductor lying in this closed loop C over which the electric field is integrated. Okay, so that is the point. Okay, so this statement is generally true for any surface and any curve, it doesn't matter. But if there lies a conducting wire along this curve C, then this electric force is going to drive a current through that wire. Okay, so EMF drives a current through a wire, and that EMF is basically defined as a force per unit charge integrated around a closed loop. Okay, if you notice in this definition of EMF, I have not mentioned that it is the electric force per unit charge. Although if I integrate this local equation here, then what I get is basically it's the integrated version of the electric field. But while defining EMF, I am defining this to be the force per unit charge. That force can be electric as well as magnetic. Okay, in general, when I define EMF, it can be electric as well as magnetic. But it so happens, if I take this equation and integrate, then I get the electric force per unit charge on the left hand side, and that integrated along some closed loop, and this is equal to the time dependent. This is equal to the time derivative of the magnetic flux which is passing through a surface which is enclosed by this closed loop C. Okay, so very good. With this subtlety pointed out, let me now state Faraday's law as it was, observed by Faraday. Faraday observed that this EMF, which is produced in a current carrying, which he saw here, it was produced in a current carrying conductor due to a changing magnetic flux, d phi dt. That EMF is proportional to that. Is not only proportional, it's equal to that. And basically, there is a minus sign here. Okay, so the minus sign, what this minus sign means, this minus sign also has a name. It's called Lenz's law. Okay, this sign. So basically, what it tells us is, look, in this dynamical situation, of course, when you imagine. So as I said, here up to here, this equation is valid whether or not there is any current carrying conductor or not. Okay, this equation is valid. Now let's say there is some current carrying conductor and there is an EMF which is generated. The question is, now this EMF will drive a current, but this current will be in what direction? Okay, and this sign tells us what that direction of the current would be. So basically, if there is a current flowing through this current carrying loop, let's say there's some conducting wire here, and there's some current carrying, there's some EMF which is generated because of this local equation here. There's some changing magnetic flux inside the surface. There's a time dependent magnetic field inside the surface, and because of that, there's a changing magnetic flux through the surface. Okay, and given that scenario, there is a non-zero, d phi dt is non-zero, and so basically there's some EMF. This EMF is going to drive a current, and this current in turn is going to produce a magnetic field. So the EMF would be produced in a direction which will give rise to a magnetic field, which this EMF is going to be produced in a direction which will first give rise to a current, and that flowing current will again give rise to a magnetic field, and the direction of that magnetic field will be in such a direction so as to oppose the change. Okay, so as to oppose the initial change in the magnetic field. So basically, to summarize, I know I said that maybe in a complicated way, but you see, if there is a magnetic field which is pointing in this direction and it is decreasing in magnitude, then the current will be set up in a direction so that there is a magnetic field in this direction as well, which kind of opposes the decrease because there is now a new magnetic field in this direction. Okay, so that is what this sign tells us, that the change in magnetic flux is opposed by the EMF. So this is what it means. Okay, but as far as the integral of this statement is the integral of this equation is concerned, this is true with or without any flow of any current. If there is a current carrying conductor, then also this statement is true. If there is no current carrying conductor, in empty space magnetic field is increasing, decreasing, then there is an associated electric field with it, and that should satisfy this equation for every surface that you are drawing in the region where the magnetic field is increasing or decreasing. Okay, so this is what this equation stands for. Okay, this local equation stands for. But as we will soon see, that written in this form, where this E is basically the force per unit charge rather than the electric force per unit charge, then written in this form, this equation has more content than just this local equation here. Okay, so that we will see very soon. And so that is the claim that I am making, that Faraday's law is, as Faraday stated it, in terms of the EMF and the changing magnetic flux, this is more general than this local version of this law, which is this curl of E expression. As we saw, that this curl of E expression is consistent with that, because if you integrate the curl of E, then you get a statement which says force per unit charge, the electric force per unit charge is equal to the changing magnetic flux. Okay, the changing magnetic flux, and if there is a time derivative, if there is a time dependent magnetic field, then there is a changing magnetic flux, and that basically is captured by this equation here. Okay, now with this fact in mind, that perhaps this Faraday's law is more general than this local statement, if we now think of the EMF as force per unit charge integrated, line integral of force per unit charge, and that is not only the electric field but also the magnetic field. So the electric and the magnetic force, the electromagnetic force per unit charge, line integral of that, if that is the EMF, then in that case this equation also takes into account something which is called motional EMF, and that is what we are going to discuss. And this statement, as written, is true for both the cases, whether or not there's a electric field due to a changing magnetic field and that drives a current, or because of the motion of a wire through a constant electric field, there is a change in flux, that also can drive a current because of the magnetic force, as we will see now. Okay, so in order to demonstrate, what I just said, let us consider first two simple, very, very simple examples. Okay. So the first simple example that I want to consider is this. Let's say, there is a circular loop like this. Okay, there is a circular loop like this, and there is a magnetic field which is uniform, but it is decreasing. Let's say at some time t, the magnetic field starts decreasing. Because this is a wire loop whose area is constant, and the magnetic field is decreasing, therefore the flux through this surface starts decreasing, because flux through this surface is essentially magnetic field times the area of the surface in this configuration. Okay, so then the magnetic field starts decreasing, and therefore the flux of the magnetic field through this surface enclosed by this loop, that flux also starts decreasing, so it's less than 0. Okay, ddt of d phi dt is less than 0, which says that phi is decreasing with time. Now that would imply that there is a EMF which is greater than 0, and this EMF would drive a current through this loop. This current is going to, again, as you can see, produce a magnetic field, and this magnetic field is in this direction, which kind of opposes the decrease and tries to increase the magnetic field in this direction. Okay, so that is the idea, that is the statement of the sign. So EMF is in such a direction which will drive a current that produces magnetic fields in the same direction, because the magnetic field here is trying to decrease. Okay, so that is the statement of the sign or Lenz's law, and this is the situation, the first example that I was trying to describe. Now you should understand that this example is completely consistent. Here when I write down Faraday's law, d phi dt equal to minus epsilon, then this is completely consistent and a consequence of this local form, curl of E equal to minus del B del T. Okay, in this example, this is exactly what is going on, because you see, what is going on is there is a magnetic field which is changing with respect to time, and this magnetic field is generating an electric field along this loop. Okay, it is also generating electric field along any other loop, but the magnetic field is generating some electric field along this loop, and basically because this is a current, this is a wire, conducting wire, because there is an electric field, that electric field drives the electrons inside the wire and tries to generate a current because of this electromotive force, or this EMF, which is basically the electric field, electric force per unit charge, line integral of that. Okay, so that would basically try to drive this current. That electric field produced because of a changing magnetic field would try to drive this current, and this example is completely consistent with the local equation curl of E equal to minus del B del T. Okay, and this is also consistent with the Faraday's law, and so that is the reason why this local equation, this particular Maxwell's equation, is also sometimes referred to as the Faraday's law. Okay, now let us consider the second example. The second example is here. Let's say you have this is some conducting wire like this, and you have a uniform magnetic field which is so this is, let's say, in the xy plane, this wire lies in the xy plane, and along the z direction there's a uniform magnetic field which is pointing upwards. Okay, now here you put a rod, which is again a conducting rod. Okay, and you start gliding this rod and start to decrease the area of this loop. Okay, now if you try to do that, then you see, even in this case, the flux through this loop is going to change. Why is the flux going to change? Because now the magnetic field is constant, it's not changing with time, but the flux through the loop actually starts decreasing with respect to time because the area of the loop decreases as the wire moves with constant velocity along this direction. This rod moves with constant velocity along this direction, and therefore there is a change in area. And because flux is basically magnetic field times area, and because area is changing, therefore you have a changing flux through this loop here. Okay, so very good. So therefore here we can say that there's a change in flux. This one I wrote later, but let's say d phi dt, this is b dA dt, and because the area is decreasing, and the area is decreasing at the rate u times d, because u is the velocity, is the magnitude of the velocity of this rod. So this u times d is the rate at which the area is decreasing, because you see the decrease is basically given by this, let's say in some infinitesimal time, u delta t, it moves. So this will be the area that gets decreased. So this is d. Okay, so this I should write perhaps. This distance here, this distance is what I'm referring to as d. Okay, so this in this case, therefore, minus u times d is basically the change of magnetic flux through this surface as the rod moves with a constant velocity u. Now let us consider the force per unit charge integrated over the rod. But now it will be the magnetic force per unit charge integrated over the rod. You see, the rod is moving in this direction. There is a constant magnetic field in this direction. Therefore, the charged particles inside the rod, particularly the free electrons, they will essentially experience a force in this direction, in the direction of the rod, right? Okay, so basically, the force per unit charge integrated over the rod, so that will be like u times b, because these are orthogonal. So there is no, like, u cross b is u times b. Okay, so these are orthogonal, and times the line integral over this up to this region. So this is u times b times d. Okay, because it's the line integral of the force per unit charge. Okay, so that is u times b times d. And here in this experiment, we see that the force per unit charge again, this EMF, this is again equal to the change in magnetic flux. Now here the physics is completely different. You should understand that in the earlier case, in example 1, the change in magnetic flux was created because of the changing magnetic field, but the area of the loop was constant. But here the change in magnetic flux is caused by the change in area of the loop, and because that is changing, there is a force per unit charge on the current carrying, on the charges present in the conducting wire, and this charge is this force is magnetic force, and because this force is magnetic force, therefore, this magnetic force can actually push the charge carrying conductors and give rise to a current. And this kind of EMF is sometimes referred to as motional EMF. But you see, it's the same Faraday's law. The same expression is valid. It's the same expression. If you write here, E is basically the EMF, or the force per unit charge. It's the Lorentz force per unit charge, both electric and magnetic, and the line integral of that. If that defines for you the EMF, then here this d phi dt should also include both the change in flux due to changing magnetic field as well as the change in flux because of the change in area of the loop that you're talking about. Okay, so both these effects are actually contained in this expression here in this statement of Faraday's law. One of these statements, which corresponds to this example 1, is basically corresponds to the fact that curl of E equal to minus del B del T, because in that case there is a change in magnetic field. But in the other case, as you can see, there is no change in magnetic field. So this equation is not what gives rise to Faraday's law here. It's basically the idea of motional EMF, which is giving rise to Faraday's law here. But Faraday's law is something which is equally valid in this scenario, as well as in this scenario. Okay, in both the scenarios, Faraday's law is equally valid. So basically, this statement of Faraday's law written in this way has a bit more than the local equation, which is also sometimes referred to as Faraday's law, this equation. Okay, this integrated equation where you're talking about EMF and change of flux, this somehow has more a little more physics than just this local equation which says changing magnetic field creates electric field. Okay, So with that in mind, we will proceed with a general proof of this statement that I made, that this in general, so here I demonstrated this fact in two examples, right? In two simple examples, I demonstrated that this E equal to d phi dt works in both the cases. But now we are going to derive this Faraday's law, this form of Faraday's law, employing both the local form of this equation, curl of E equation, as well as the idea of motional EMF. We are going to take them together and we are going to derive this most general form of the Faraday's law in a general situation. Okay, now let's do that. And for that, again, let us imagine that there is some conducting wire like this, which is this loop, which is C, and basically the loop is moving, and it is moving such that its area can also change. Okay, so S is the surface at time t, and S at t plus delta t is the surface of the loop at time t plus delta t. Okay, and this S can be a different surface than the surface at time t. Okay, so in general these are different surfaces, and the loop can be moving. So at time t the loop was located here, and at time t plus delta t the loop can be located here, and the surface area of the loop can or the surface area enclosed by the loop can also change with respect to time. That is taken into account here. But also, apart from all this, there are these magnetic fields which is passing in this region, and this magnetic field is also time dependent. So both the effects are happening together, that the loop can increase its area and the magnetic field is also time dependent. So both are going to contribute to the change of magnetic flux through this loop with as we move along time, or with time there's going to be a change of magnetic flux, and that change will have contributions from both the changing magnetic field as well as the changing area of the loop as we time evolve. Right. So this change, therefore, change of flux, can be given by the flux at t plus delta t, this thing, minus flux at t. Okay, this is a very simple statement. This is the change that we want. Okay, so this is the change in flux in time delta t. Okay. So now we just write out this, the expression for the flux. So basically at time t plus delta t, we have to take the magnetic field at time t plus delta t and integrate it over a surface which is at t plus delta t. Okay, which is this surface which is enclosed by the loop. Now at t, this phi of t is simply the magnetic field at time t, and we integrate it over the surface S at time t. Okay, which is this surface here at time t, we integrate. Okay, this is the first, the difference of the two, this is the difference of the two fluxes, okay, at time t and at time t plus delta t. Now, because the magnetic field, this delta t is going to be, a very infinitesimal quantity. At the end of the day, we are going to take the delta t going to zero limit. So we are going to work only in linear order in delta t, so that we can find d phi dt by taking the limit delta t going to 0. Okay, so that is our goal. So if we want to take that limit, then we see that we can take this expression for the magnetic field and do a Taylor series expansion, right, in terms of delta t. So if we did that, so of course the magnetic field can also have some spatial dependencies. I'm just suppressing the spatial dependencies and only showing the time dependence here. Okay, it can have a complicated spatial dependence. It can be a non-uniform magnetic field, doesn't matter. But this argument would apply if the magnetic field is also uniform. Okay, but it just need to depend on time, right? In fact, this will also apply if it doesn't depend on time. I mean, that is also there. Okay, because let's say if the surface is just changing, let's say at a constant magnetic field, constant in time and space, then basically at the flux at this instant would be the same magnetic field integrated over a different surface compared to this one. So still this difference will not be zero. Okay, that I want you to appreciate. Very good. Now if you take this magnetic field and expand it in a Taylor series expansion in delta t, so then the first two terms I have written down here. The first one will have a first derivative of the magnetic field and so on. So then now we get essentially there will be three terms. One term will be this magnetic field at time t integrated on the surface t plus delta t. This is one thing. The second term will have an argument which is the time derivative of the magnetic field, but it will be multiplied. The integrand itself is multiplied by delta t. Okay. Now because the integrand itself is multiplied by delta t, therefore we can safely ignore the delta t in the limits of the integral. Okay. So basically, therefore, this second term, where this should have been perhaps st plus delta t, this, as far as this integral is concerned, because the integrand has this delta t order, therefore we can just ignore this part in this s of delta t. Okay. So that is this thing. And then of course then this is this term which was there, and that remains as it is. And of course, the things that we have neglected, these dots plus, this contribution from here, these are going to be of order, of quadratic order in delta t. Okay. So how do we see that? Let us just, see that, try to see that in this simple example. Okay. Let's say you have an integral x times epsilon, where epsilon is small, and you want to integrate that between 0 and a plus epsilon. Okay. Then you will see that if we do the integration, then you will see that this is epsilon x square by 2, 0 to a plus epsilon. And if you are interested only up to terms which are linear order in epsilon, then this is epsilon a square by 2. Okay, this integral comes out to be that. Now notice that even if we drop the epsilon in this limit and integrate it from 0 to a, we get precisely the same answer. Okay, so at linear order, this little shift in the integral limits with respect to epsilon does not matter if the integrand itself is linear order in epsilon. Now here also a very similar thing happens. Here the integrand itself is linear order in epsilon. Now, as far as the surface is concerned, there are maybe two integrals like this. So even in case of two integrals, it will not matter if it doesn't matter in one integral like this. In case of two integrals also, it will not matter. And therefore, I can drop the delta t from this surface and just consider the surface in this integral at time t equal to, the surface at time t. Okay, that will be fine. If we consider the surface at time t plus delta t, that will be different from this answer by terms which are of the order delta t square. Okay, anyway, which we are not keeping track of these terms which are of order delta t square. Okay, so up to linear order, this is the expansion. And again, I have written terms only up to linear order, just rewritten what we had there. And now if we take this expression and if we try to divide this, if we try to divide this expression our objective would be to ultimately take this factor of delta t out, divide this by delta t, and then take the limit delta t going to 0, so that this gives me d phi dt. That is our objective. Okay. If that is our objective, let us write, this was our diagram here. I have just reproduced that diagram here just to make the discussion convenient. So here, as you can see, that there's this integral of the magnetic field over this surface. So basically, the normal to the surface is denoted by n3. Again, the normal can be different at different places. Doesn't matter. I'm just schematically denoting it by n3. So this is the normal to this surface, S at t plus delta t. Okay, so this will be b dot this normal. And so this one is basically if n2 is the normal in this direction, inward direction, for the surface S of t, then this is going to be n1 for the surface S of t. Okay, so similarly, for the surface S of t, this one also is going to be along n1, but this is not so important to keep track of, so I am not writing it explicitly. Okay, so this term remains as it is, and here I have carefully kept track of the normals. Okay, so here both the normals, this one and this one, is pointing in the same direction. This is what we mean when we take the change of, when you consider the change in flux, because we want the change in flux in the same direction. So we consider the area elements also in the same direction, in the direction of n3 here and in the direction of n1 here. Now we can shift this and make this into n2. N2 is just minus n1, okay, in the opposite direction, as you can see in this diagram. So N2 is just minus N1, and we can but now it points in the opposite direction. Okay, this N2 now points in the opposite direction. So therefore we'll have a minus sign here in this expression. We will have a minus sign here. So here we are essentially this term, we are talking about this term here. This term becomes this term here, and now after the flip N1 to N2, this minus sign flips and becomes a plus sign here. Okay, so now this becomes a plus sign. Now this, as you can see, is basically the integral of the flux through both these surfaces. This one surface on top and the surface in the bottom, both these surfaces, you have the flux through both these surfaces. Now notice that along with both these surfaces, if I add the surface at the side, which I am denoting by sigma, this green region that I have drawn here, this green region is the surface on the side. Okay, and this surface I have denoted by sigma. If I add this surface to this S of t plus delta t and S of t, then this three surfaces constitutes a closed surface which encloses a volume V, right? So these three surfaces, we can, so these are integral over both the surfaces. Now we can have all the three surfaces and subtract the surface, integral over sigma, which is this side surface here, this side surface here. This side surface integral we are removing, because these two surfaces together, these three surfaces together form a closed surface, which is this one, right? So basically this integral has three terms, 1, 2, 3. I have subtracted one, then I'll be left over with the two terms here. Okay, that's all I have done. Now it's very clear what to do, because this is a closed surface integral and it's a closed magnetic flux through a closed surface. That can be written as the divergence of the magnetic field through the volume that is enclosed by the closed surface. This is just by divergence theorem, and as we know, since the divergence of B is 0, this has to be equal to 0. So we are left over only along the integral, only with an integral on this surface sigma, which is the surface at the side, and then there's a minus, there's a del B del T. Okay, of course del B del T we can take again Maxwell's, this local equation. There's an input from there. We can take this local equation and convert del B del T into the curl of E, okay, using this Maxwell's equation. And once we do that, then this becomes a surface integral of curl of E times delta T. Okay, again this surface integral of curl of E again now becomes the this surface integral of curl of E, which is at S of t, that surface integral, that becomes that is times delta t, that by Stokes theorem now becomes a line integral, where the line integral is for a closed loop, and this closed loop is the loop of this surface at time t. Okay, this is the C of t at time t. This is the loop. This is the loop, position of the loop. So this is the line integral that needs to be performed over the loop at time t, and this C of t is basically the boundary. It is the boundary of S of t that is equal to C of t. Okay, so this is by Stokes theorem. This step comes about. Now, so this is 0 as we argued, because divergence of B is 0 by Maxwell's equation. And now we have to understand what this means for this magnetic field to be integrated over the side surface. Okay, now in order to understand that, let us try to look at this expression, and so basically, when we say that it is this flux through the surface at the side, we have to take into, because we have applied this divergence theorem, so we have to take the outward pointing normal. So this N4 is pointing outwards. Okay, so in this integral, this ds vector, this ds vector has to be in a direction, this area element has to be in a direction which is pointing outwards compared to the volume inside, right? So now if we consider this diagram, and you see this loop, let's say, is moving with some velocity vector u. Okay, this is, this can be in arbitrary motion. So again, the velocity vector can be different at different points on the loop in general, but let's say it's moving with some arbitrary velocity vector u. Okay, so in this location would have moved in time delta t to this point. The displacement vector therefore would be u vector times delta t in this direction, and this vector would be on the side surface which is of interest to us. Also, this this infinitesimal length here, this is given by dx, and this dx is along the loop of this base loop of interest. Okay, this is this dx is along the loop which is the boundary of the surface at time t. Okay, this is the c of t, and this dx vector is along this loop. So you see, now if we take this u and this x, okay, and if we perform a dx cross this vector, this displacement vector, dx cross this vector, then that will give me a outward pointing normal in N4, okay, and that will also give me this area element, which if I integrate over this whole loop now, I will get the area element of this. I would have performed the integral over this whole side surface sigma. Okay, so that is the idea, and that is what we are going to do. So here we are going to take this ds, which is basically dx times this displacement vector, and so this is the area. This is the area element on the surface sigma, which is pointing outwards. Okay, and now if we take this and plug it back in here, then this will be this essentially is dot b. That is the flux. Okay, this is the area element. This is the flux. And this remains as the line integral of the electric field. Okay. Now this expression here, this is dx cross u times b, and hang on. So I think I have missed delta t here. Let me put that in. So there's a delta t here, and there's a delta t here. Okay. And now I divide by delta t everywhere. So if I divide by delta t, this, and take the limit delta t going to 0, this delta phi becomes del phi del t. This becomes the derivative, and now I am left with two terms here. One term is this term from the electric field, that is simple, but then there is another term which is dx cross u times b. Again, this delta t moves out in the when I divide by it. So this term, we can repackage. So we can. I have just used this definition of cross product using the epsilon here to rewrite this term in this form. We can write it as u cross b dot dx. Okay, this term. Okay. Now as soon as I do that, you can now see what is going on, that both these integrals are now integral over this this loop c at time t. Okay, and this line integral, both are line integrals, and both are line integral of force per unit charge, because here we have the electric field and here you have the velocity of the loop cross the magnetic field. Okay, so please remember that this is the velocity of the loop. Okay, and so it's not the direction of the current. This is the velocity of the loop. Because of the moving loop, the let's say the charge carriers inside this wire can move only in this velocity because it's moving in this way, and then they experience some force, and that results in the current. That is the idea. Okay, that results in the EMF, which results in the current essentially. Okay, so this therefore is basically the expression of the EMF that we have defined. It's the Lorentz force, the full Lorentz force, the electric and the magnetic, the full Lorentz force per unit charge integrated over a closed loop. Line integral of that over a closed loop. That is what the EMF is, and that is clearly given by the change in magnetic flux, where there are two effects in this change. One effect is the change in magnetic field itself with respect to time, and also it also takes into account the effect that the area of the loop itself can change with respect to time. Okay, so both these effects are contained in it, and we have proved in most generality that this general expression for Faraday's law, which has two things. One is basically this local equation, okay, equal to minus del B del T. That thing is there, and plus we have Lorentz force. Okay, both the things, both this physics is there in this expression of the Faraday's law. Okay, and there are essentially two effects which are present in this Faraday's law, and both of them combined gives you this compact law, which is super useful. Okay, it's very important to remember this Faraday's law, therefore. Okay, very good. Now, having finished that discussion, we will move to one discussion that was pending when we discussed magnetostatics, and this discussion was about the energy in the magnetic fields when we have static magnetic fields in magnetostatics, what is the energy in the magnetic fields? Okay, so that we understand that, you know, what is the energy in the magnetic fields, that we calculate by calculating the work done in producing a steady current which produces those magnetic fields. Okay, this is what we want to do. Okay, so in order to do that, let me start with a definition first. You know, this definition is that of inductance, and it is a property of a material. Okay, let's say, you know, there is a conductor, you know, current carrying wire, or, you know, there's a wire of some material, and the inductance is basically a property of some, you know, material which has let's say some charge carriers that can move around. Okay, and, you know, in which a steady current can be set up. You know, those you know, that kind of a material has this property which is called inductance, and this property is given in this way, that let's say there is some flux phi which is you know, passing through this through some integrated area where this conductor, or, you know, this material lives, and this is basically the magnetic flux. Okay, this is the integral of the magnetic field, and this divided by the current which is flowing through this conductor, or through this material. That ratio is called the inductance of the material. Okay, this is a property of the material. Okay, so this is inductance is what is the ratio of magnetic flux to the current which is flowing through a particular, let's say, you can imagine a current carrying wire for that matter. Okay, in this case. So now, with this in mind, with this definition of inductance in mind, we also have Faraday's law, which says that force per unit charge is basically given by minus d phi dt, and basically phi is given by L times I. L is a property of the material, it's a constant, so I can bring it out. So basically EMF becomes minus L times di dt. Okay, so this is just a rewriting of Faraday's law given this definition of inductance. Okay, now so basically if we now consider, let's say, an infinitesimal charge which is being moved around to set up a current I, let's say. Okay, ultimately the current I will be a steady current, but while it is being set up, you know, there can be some time dependence, and this is what, you know, this is capturing. Okay, while the steady current is being set up, you know, there can be some time dependence of the current, and basically, you know, that the EMF to drive that current is given by Faraday's law, and the proportionality constant is the inductance. Okay, so so basically, if we now take this infinitesimal charge, consider the infinitesimal charge that is being moved around to form this current I, you know, that infinitesimal charge will be like, you know, I times del t, because as you know, this current is basically like you know, charge per unit time, you know, flowing through a surface. So the infinitesimal charge, you know, that is responsible for this current is given by I times del t. Okay, in, let's say, some infinitesimal time delta t. Okay, now if we have this statement for delta q, then we can ask that what is the work done in performing the, you know, in moving this infinitesimal charge so as to ultimately form the steady current I. Okay, what is the total work done? First, let us ask what is the infinitesimal work done in moving this infinitesimal charge in time delta t. Okay, so that infinitesimal work would be given by force per unit charge, line integral of that, essentially, you know, that is the definition of work done, times the infinitesimal charge that is there, you know, delta q. Okay, so this comes from the definition of EMF, that is force per unit charge, line integral of that, and we know that work done is basically force line integral of that, minus of that, because we are doing work on the system. So minus of force dot you know, line integral, you know, that gives us the work done, and here we know that force per unit charge of that line integral is giving us this EMF. So EMF times infinitesimal charge, that will give us the infinitesimal work that is being done. Okay, so basically, therefore, delta q is I times delta t. So the infinitesimal work which is done in time, you know, delta t, where delta t tends to 0, you know, dw dt, you know, this is simply equal to minus the EMF times I. Again, we know that this EMF during the process when the steady current is being set up, once the steady current is set up, this di dt is 0. But we are talking about the process in which the steady current is being set up. So during that process, you see, now we will consider this expression and plug it in here for the EMF. So if we do that, we see that we get, I can directly, move into this expression. So EMF is minus d phi dt, so that minus sign cancels, times I. And d phi dt is basically here, if I use the inductance formula, this is some ddt of L times I. And this is basically, we can just, so this is basically L is a constant which you can pull out. And this is di dt times I. Di dt times I can be written as half of L times di square dt square. Okay. So, sorry, di dt. You know what I mean. Okay, sorry. So here, as you can see, we can pull this out of this pull L out. I hope this step is clear. So we can pull L out, and we can write this as some d, I times. We can write this as some I times di dt. I times di dt during the process, and this I can write. I times di dt I can write as L by 2 times di square dt. Okay, because this differentiation will bring down the factor of 2 and it will be I dt. Okay, this is just an identity. Okay, so this is the expression. Okay, and again this half and L I can bring inside the integral and perform an integration in time from 0 to t, let's say, where finally the steady current is set up. Okay, that is the idea. Okay, so the amount of work done, so infinitesimal work done in time delta t is basically this. And now I want the complete work done in setting up the steady current, which is the final, steady current, right? So if you like, we are taking this expression and writing an expression like dw, infinitesimal work done in time t is equal to half L di squared dt square, sorry, di squared, sorry. You can totally write, take the half L inside, and you can write this as some d of half L I square. Okay, and now you integrate this from 0 to total work done, and this you integrate from 0 to the steady current value. So this is the steady value. Okay, this is the steady value, and if you do that, then you get this expression for the total work done. Okay, now if you get this expression for the total work done, then you can perform the following manipulation. You can again write the L times I. So now I want to eliminate I. Now once I have set up the current, set up the magnetic field using some current, then I want to make my analysis or this expression for work done independent of L. So I will eliminate L. So if I eliminate L, then this expression becomes half of I times phi, where phi is again the flux. So remember, our expression L was equal to phi by I, right? So because L was equal to phi by I, therefore you can just substitute it here. You will see that this is I times phi, and then this is I times B dot ds, which is the expression for the magnetic flux through some surface S, which is enclosed by the loop through which a steady current is set up, let's say. Okay, now again this B you can write as curl of A. Okay, here from this step, this B you can write as curl of A, because that by definition is the expression in terms of the vector potential. And once you write it as a curl of A, then you can use Stokes' theorem to write it as a line integral. So essentially the work done reduces to half of I times the line integral of the vector potential of the magnetic field. Okay, that is the work done. Okay, so now this becomes very easy, because then it's, one can simplify this further, because that in general you remember this thing that we had discussed before, that I times line integral of a current carrying loop is basically the volume integral of a, in general, these are like, this is the point, in general this will be the expression for the work done then. Okay, if you have many current carrying loops, let's say, forming some kind of a current density, then basically you can do this exercise for all such loops, and then the total work done, you can just perform the integration over all such loops and convert this into integral of volume integral of the current. You remember, volume integral of the current is basically line integral of a current carrying conductor. Okay, volume integral of current density is basically line integral of a current in a current carrying conductor. Okay, so that we are using here to go from here to here, and if this is the total work done, then basically we can now you remember this is the way I had written it in the previous video on in magnetostatics. So this is exactly the same thing that we are applying here. And so now remembering again the Maxwell's equations in at the end of the day it is basically magnetostatics. Okay, so of course during the setting up the current there was this di dt, but at the end of the day this current is a steady current, and this current is set up sets up a steady magnetic field, time independent magnetic field, and therefore in that case we will have the Maxwell's equations in magnetostatics. If you remember, then curl of B is equal to mu times J, and that value of J we can replace from that Maxwell's equation. Okay, this is the Ampere's law, local version. We can take that and replace it here, and if we replace it here, then we'll get A dot curl of B. Again, here we can do a manipulation. We can take A dot curl of B and write it, this is like a vector identity, write it as this is the divergence of A cross B and B dot curl of A. Okay, so the divergence of A cross B, again, this is the volume integral of the divergence of A cross B. So therefore, you can convert this into a surface integral, this is the surface of the volume, surface integral of A cross B. Now, if you have again, if these are localized charge densities and you are integrating over the whole volume of full space, where this is like the sphere at infinity, then basically the magnetic field will vanish on the boundary, and that will be a natural boundary condition, because nothing goes over to infinity if you have localized current densities. Then this will vanish on the boundary. Okay, this will vanish on the boundary, and this term therefore you don't need to worry about. This term will vanish. Whereas in this term you see this becomes B dot curl of A, and again curl of A is B again by definition. So this just becomes B square. Okay, so again the total work done we see in the magnetic field, in the magnetostatic fields as well, okay, is given by B square. You remember for electrostatics, this work done, or the energy which is stored in the electric fields, was given by E square, and the energy which is stored in the static magnetic fields is also given by B square. So if you have static electric fields and static magnetic fields together, then you will write down something like E square plus B square. This total energy will have this form, that E will have this form, this total energy will have this form. It will be half epsilon naught, here this will be a mu naught, sorry, epsilon naught E squared integral of that d cube x, sorry, let me write it compactly. Yeah, so basically what I want to write is half of integral d cube x E squared epsilon naught plus 1 over mu naught b square. Okay, this is exactly what you will have what you have found in both electrostatics and magnetostatics taken together. Now, as you can see that we haven't involved time dependent dynamics. Ultimately the currents are steady currents, and we are talking about electrodynamics and electrostatics and magnetostatics. There is no dynamics in this expression of energy. But as we will see later, that this expression for energy is actually very general, and it is applicable even in dynamical situations. Okay, so this expression for energy, remains very general, and it remains very general. So this is just half. There's this factor of half integral, the volume integral, and then epsilon naught E squared plus 1 over mu naught B squared. This is actually, as we'll see later, is the expression for energy in complete dynamical situations as well. Okay, although we have argued for it till now for electrostatics and magnetostatics separately, this is going to be the expression for energy in complete dynamical situations as well. Okay, we'll see that. Very soon we'll see that. Now, as I said, but in the electrostatic fields and in the magnetostatic fields, therefore carries some energy, and this energy is given by the square of the fields integrated over some volume. That is the total energy contained in the fields. Okay, so that is a very important result, and we can use that result to calculate the energy in the electric and magnetic fields. Okay, so the electric and magnetic fields carry energy just like particles carry kinetic energy or potential energy. Like that, the electric and magnetic fields also carry energy, and as we will see later, they also carry momentum and angular momentum. We'll soon see all of that very soon. So there's not much difference between the classical mechanics of particles and classical mechanics of fields. Just that while talking about fields, you have to have a continuum in mind, that these are functions over space and time. But as far as their dynamics is concerned, you can have all these quantities, energy, momentum, etc., defined for the fields as well. Okay, very good. So one last topic that I want to discuss in this video is this idea of the displacement current, and this has got to do with Ampere's law. Okay, so as we have seen in magnetostatics, that Ampere's law is written in this form here: curl of B is equal to mu naught times J. Okay, this is the Ampere's law. And then if we integrated it, then we will take the, we will consider the line integral of the magnetic field. We can consider the line integral of the magnetic field, and this line integral of the magnetic field should be given by the current enclosed by a surface whose boundary is basically this line C. Okay, this closed loop C. So the line integral of a magnetic field across a closed loop should be equal to the current enclosed by the closed loop, or the current which is passing through the surface, any surface, that is the main point, passing through any surface through that, whose boundary is this closed loop C. Okay, this we have demonstrated before in magnetostatics, and we have seen that for this to be true for any surface, the divergence of J must be equal to 0. Okay, and that was true because charge density charge density itself was 0 in magnetostatics ansatz, or there was no time dependent charge density. If we put together magnetostatics and electrostatics, there is no time dependence. So in this continuity equation, in general, where del rho del T plus divergence of J equal to 0, in this continuity equation, this term was simply absent. And because this term was absent, divergence of J was equal to 0, and we could use this divergence of J equal to 0 to show that any surface, if we considered, which is enclosed, whose boundary is this loop C, then this gave us the right value of the current on the right hand side. Okay, so the left hand side and right hand side matched if we considered any surface. But in a dynamical situation, this can fail miserably, as we'll see here. Okay, so so we'll just demonstrate that in an example. So in an example, if we try to consider, let's say we consider the following circuit where there's a capacitor here. Okay, as you can see, there's a capacitor here where the charges in the capacitor is oscillating as a time dependent or alternating current is passing through this loop. Okay, so this current carrying a wire has a source which is an alternative current source, and this can drive a current through it because it's an alternating current, and the charges on this plates of a parallel plate capacitor, that is going to alternate with time. Okay, and that is going to give rise to a current in this loop here. Now the interesting thing happens if you want to find, so this current as when it moves, then it will create its own magnetic field, right? As you can imagine that here the magnetic field will be created, so the current moves in this way, so the magnetic field will be created in this way, right? If I am right. Okay, so the magnetic field, so that is the direction in which the magnetic fields would be created. So now if we consider the magnetic fields which are being created by this flowing current, and if we consider this loop here, this loop C as indicated, okay, this is C, okay, then we consider the line integral of the magnetic field on this loop, on this closed loop. Okay, so that will take some value. Now in order to find what value would it take using Ampere's law, we can close this loop off with the surface S1, and we can find the current which is flowing through this surface S1. Clearly that current is I of t. Therefore this line integral of the magnetic field would be equal to mu naught times I of t. Okay, this current is I of t if we consider the surface S1. So the line integral of the magnetic field which is a fixed quantity by the way, okay, that would be given by mu naught times I of t, okay, because that's what Ampere's law tells us, that you consider a surface which is closed and you consider the current moving through it, and this current is basically I of t, and therefore it's mu naught I of t. But Ampere's law not only tells us that, it also tells us we could consider any surface of our choice. Okay, so just like we could consider this S1 surface, we could also consider a surface which is like the surface of a pot. Imagine that this is like a pot, okay, inside. So it just goes through the capacitor plates like this, and then it shares the common line C with surface S1. So this is the surface S2, which is shaded in yellow, and that kind of goes through the plates of the capacitor, and therefore that is another surface which is S2, and expectation from Ampere's law would tell you that this if we consider this surface S2 as well, you should get the same answer. But as you can see clearly, we don't get the same answer because there is no current which is flowing through the plates of the capacitor, right? There is no current which is flowing through the plates of the capacitor. It's only the charges here that are fluctuating. Okay, plus Q, minus Q, these charges on these parallel plates that are fluctuating, but there is no current which is flowing through the capacitor because there is a gap in between. Okay, so, and the surface is precisely passing through this gap to ensure that there is no current has moved through this surface S2. So we will see that the same quantity, if we consider S1, then it will be like, the same quantity will be mu naught times I, whereas if we consider S2, then the same quantity will be 0. Okay, so it's not possible, it's giving up, so somehow in this time dependent scenario, okay, where there is accumulation of charge, this divergence of J is not equal to 0 anymore here. Okay, in that situation, therefore, we see that Ampere's law as stated in the integral form, that kind of breaks down. Okay, so therefore we need some kind of a some kind of a modification of Ampere's law in the dynamical situation, okay, which will cure us of this problem. And what is that modification? And this modification was essentially introduced by Maxwell, and that is to introduce this term which is del E del T in this equation, which is this also referred to as Ampere's law. Okay, this local form of this equation has also, along with this term mu naught times J, we also have this term epsilon naught times del E del T. Somehow this is known as the displacement current for historical reasons, but this is essentially a term which keeps track of the changing electric field as well, along with the current in this local expression for the curl of B. Now if you have this term, and if we integrate it over let's say a surface S, firstly we integrate it over a surface which has a boundary which is C, then by Stokes theorem this becomes the line integral of the magnetic field over the surface over the boundary C. Okay, so again, this is some surface S and this is some C, okay, del S equal to C, okay, that is what it is. And so this part of the equation becomes this, okay, the line integral of the magnetic field. But here, as you can see, this part of the equation, the part which is mu naught J, that becomes the current, okay, mu naught times integral of the J through the surface S. But apart from that, there is a contribution from this displacement current as well, which tells us that we should keep track of del E del T, and we should try to integrate, take that del E del T and dot it with the surface and try to integrate the flux of this del E del T also through the surface. Okay, so that we need to do, and this surface is again a surface whose boundary is this C, on which we are performing this line integral of the magnetic field. Okay. So again, we can go back to this problem. When we consider the surface S1, there is no changing magnetic field there. So of course, this answer is right, mu naught times I, that answer is right for surface S1. What happens for S2? Of course, there is a plus Q and minus Q charge on the plates of the capacitor, and the electric field inside the capacitor changes with time. So there is the del E del T in this region inside the capacitor. And let us try to see, so of course there is no I in this, contribution from the current on this surface S2, but there is definitely a contribution from the changing electric fields on this when we consider the surface S2. Okay, so let's see how that goes, how that contribution goes. So basically when we consider S1, then this is mu naught times I as it was before. But when we consider S2, then there is no contribution from current, but there is a contribution from del E del T. So if you are, I'm sure all of you have done parallel plate capacitors before. So, I'm not reviewing it. You can use some nice Gaussian surfaces here to find out what is the electric field inside a parallel plate capacitor. And that would tell you that it is given by the charge, the total charge on the plates, okay, divided as a function of time, divided by the area of the plates here, and epsilon naught. Okay, this is the total electric field which is produced between the plates of a parallel plate capacitor. Okay, now this electric field, therefore the time derivative of the electric field is basically the caused due to the fluctuation of the charge. So the time derivative hits the charge accumulated here, and that basically changes with time. Okay, because there is alternating current flowing through the circuit, therefore this charge accumulated on the plates of the capacitor also changes with time. Now basically this dq dt is precisely the current which is flowing through the capacitor. So now if you take this and dot it on the surface, and then this dE dt is basically given by this quantity, and this electric field is pointing along this direction from, let's say, the positive plate to the negative plate. Of course the polarities change, if this is the alternating current, but if we fix a convention that this is the direction of E, okay, then this essentially becomes the direction of the surface, the outward pointing normal, and then these two the normals gets rid of these vector directions, and then we are left with del magnitude of E del T and this ds. Okay, and then this ds integral remains. So this is dq dt is the current which is flowing through the surface, and this integral is basically the surface inside the capacitor only. Okay, this is the part of the surface inside the capacitor. So this essentially gives me the total area, and this area cancels from the numerator and denominator here, and that leaves me with mu naught times current, the same expression as I got in the when I integrated the current on surface S1. Okay, so when we did this integral over surface S1, then also we get the same value, and when we do this integral over surface S2, then also we get the same value if we have this additional Maxwell term, this displacement current in the Ampere's law. So this example kind of demonstrates the importance of this del E del T term. Otherwise, you see, things will become inconsistent. These line integrals of magnetic field will become inconsistent if we don't have this term. This term ensures that a form of Ampere's law is still valid. That if we consider the integral of this the line integral of the magnetic field, it is given by the total current passing through this through the surface, through any surface containing this content within the loop, and plus the flux of del E del T through that surface. Okay, that has to also be considered. Okay, so this analogy of this del E del T with this current therefore probably gave it the name displacement current. Okay, and therefore that is for historical reasons. But I hope this example demonstrates clearly why this additional term, and this was this term was realized, the importance of this term was realized because of Maxwell's insight, and why this essentially completes our Maxwell's equations in some sense. Okay, that is very important. But still, even in the presence of this term, this equation is referred to as Ampere's law. So now we have more or less touched on all the equations and seen them very closely. The first one is the Gauss law that we know and love, and we have used it in electrostatics a lot, and we still use it a lot in electrostatics or even in electrodynamics. This equation doesn't have any name. This we have seen that plays a significant role is Faraday's law, but Faraday's law has in some sense a statement which is more than just this equation. The Faraday's law also contains the Lorentz force condition, okay, when it is stated in an integral fashion, when it is stated in an integral form. Okay, so and then we have Ampere's law. So Ampere's law is generally stated in magnetostatics where you don't have this term, but if it is electrodynamics, then you also must have this term, this displacement current term, and then along with that, this equation is also referred to as Ampere's law. So this is the set of equations. Now we have to proceed and study the various solutions of this set of equations.